much, Dr. Qiao, and for the nice presentation. And thank you, everybody, to come here to listen to my presentation. I'm extremely honored to presenting some of my research here. And my presentation title is From Beneath to Above Ground, Advancing 3D Crop Structure Modeling and Diverse Mobile System. Well, I would like to first apologize if I miss some details during the presentation, because I want to first give a big picture about my research. But if you want to know any of the details in my presentation, please feel free to ask me during Q&A. Okay. So first, introduce a little bit about myself. Before coming to university to work, I worked a couple years in industry, and first worked at ESPN in Disney and on player trackings, and then went to Ford Motor Company for autonomous driving. Well, autonomous driving at that time attracted quite a lot of attention. Many media reported our work. Like the photo right now on this corner, up right corner, is actually my photo on New York Times. So I'm not sure whether this side body photo is the only photo that I can be on New York Times in my life. My research is mainly on the development of AI algorithm, which involve subjects like computer vision, machine learning, robotics, and remote sensing. One of the good things as a faculty member is that I have more freedom to choose the research topics I'm interested in. A major component of my research is on developing AI system for agriculture applications, for example. Okay, so for today, there is a huge potential for algorithm in agriculture, such as disease detection, plant segmentation. In this presentation, I mainly focus on 3D crop structure modeling and assessment for the crops. IT can provide critical traits for agriculture researchers, breeders, and service providers, and farmers. My talk about 3D modeling and assessment will be from 3D aspect, and root system modeling based on mobile phones, and root modeling based on ground penetrating radar, and which are for roots as well. And the rest of the part, which is the above ground part, is actually using UAV, low cost UAV for above ground crops reconstruction 3D modeling. Okay, so first, why we want to do modeling for 3D crops. So previous research on crop phenotyping mainly relies on 2D images. The use of 3D models actually can extend the 2D information with real 3D space geometry information, such as 3D angle, 3D skeleton, real lines, etc. Therefore, it provides a more accurate phenotype information. So another motivation is that 3D crop structures can provide height, volume, structure area, leaf area index, and many other information which are closely related to the crop growth. Therefore, we can estimate the crop status and predict crop growth and with 3D structure. And also with 3D information, we can predict crop yield, which could be much more precise than compared with just 2D image analysis. As for many crop species, and the yield is highly related to the 3D structures, biomass, and the volume. And the prediction, in precise prediction, is critical for farmers to manage their crop field and their business. For example, if the prediction is much more than real yield, farmers may violate the contract to deliver. And if the prediction much more than the real yield, it may result in overstorage. Okay, so I hope this is something like, I hope I have already convinced you that 3D information for crops is very important. However, this is not easy, actually. This is not easy to accurately build 3D models for the crops. So in comparison with many other species and with many other things, and there are three main challenges that lead to the difficulty. First, crop color variance is limited. Most likely, the color and the intensity for the same crop field and the plant species is the same without much distinguishment. For example, here you cannot really see much difference in the color space. So the second thing is there are too many repeated patterns that could result in a mismatching as they are too similar. Okay, and for example here, compared with this scene, okay, there are quite a lot correct matching and in crops. Since they have quite a lot repeated pattern, and you will have many mismatching. The third one is crop usually have complicated structures. And compared with buildings and tables and most other objects, crop shapes are usually much more complex. All of those things can lead to the challenges to reconstruct the 3D crops. Okay, so that gives us the chance to make some improvement. So first, I will talk about root system modeling based on mobile phones. Okay, so already there are some previous work conducting root structure modeling. Okay, the majority of the root 3D structure is to use X-ray, CT machine, MRI, those images, which can direct output the depth and across different sections of the root images. But it requires complicated equipment and needs to set up in a laboratory setting. Okay, and for the RGB images, there are already some work as well. For example, visual hall, or people call it shape from celluloids, have been used to build a 3D model. And to build 3D models. Okay, and this type of method need to find the intersection path in the 3D space from different views. And however, this requires the accurate calibration of multiple RGB images in the laboratory, which is not really straightforward for non-imaging or sensing background people. Okay, the 3D structure accuracy also depends on the number of cameras as well. For example, here there are 5 cameras and there are 10 cameras, and you can see their accuracy is different. Their details are different as well. Okay, so everybody can see that? Can see nothing is going wrong, right? Nothing is, you can still see my screen, right?
Yeah, it's good,
okay.
Yeah.
Okay. I just want to make sure, okay. So under the same principle, and for example, researchers in UGA right now, where I'm working at, and use researchers in RIT, in my old school, they develop different kind of sensing system. For example, in this setup, and there are 10 industry level cameras, RGB cameras mounted on a robotic arm. Okay, and here there's another robotic arm with camera mounted, and they can accurately control the motion of the camera. And this dome has about 32 cameras. Okay, so well, those equipment show some promising results. They are still mainly used for professional people, professional agriculture researchers, professional remote sensing researchers, and imaging researchers. It's not likely that everybody can use it. So that is actually my target, to develop a system to conduct root structure modeling based on mobile phones that can maybe let everybody have access to. So you can use a mobile phone to take a short video or some images to reconstruct, to model the 3D structures of the plants. At the same time, extract trace from the 3D structures. Okay. So there are different work we have done, and this is one work. And overall, this is the overall training framework. So from the left side, actually, the proposed work takes images as sequences. These images are captured by the camera. At the same time, on the right side, there's IMU as a constraint. Okay, so if you don't know IMU, actually that is almost on everybody's mobile phone that right now has IMU. For example, when you drive on Google, using Google Map, using Apple Map, and you can see how much your vehicle has moved. Okay, and from this distance from this place to another place, and that is actually using the IMU. Okay, that is the basic structure. And here we use a concept that is called structure from motion. So from the camera side, we use a methodology which is structure from motion, and a process to estimate 3D structures of a scene from a set of 2D images. Briefly speaking, when the object is stationary and the camera is moving, there will be a set of consecutive images. And the object position represented by the pixel coordinate will be different. So we will analyze this kind of pixel coordinate difference, and which corresponds to the same point, and recover the 3D information, and estimating the camera motion from one position to another position as well. Okay, that is the basic idea. Using the motion of the cameras and finding their intersections, and based on the corresponding pixels. That is structure from motion, basic idea. Okay. So here we develop neural network based 3D structure, 3D structure recovery neural network. Okay. So in the left side, when we take two consecutive images as input, for example, this one and this one, and the structure from motion network is able to estimate the depth image. Okay, and the depth image is estimated from the depth network, and with another 2 or 3 images as input, actually another network, which is the postnet, can estimate the relative motion between one image to another image. Okay, and after that, actually we can recover the 3D shape of the object, which here for us is the root, actually. And then later, a bundle adjustment optimization is applied to optimize the camera pose and the depth information. Okay. So, but still, one major issue for monocular camera structure for motion is the scale uncertainty. And just from the images, we can only obtain a relative scale instead of an absolute scale. Okay. And in other words, we just know the relative size instead of the absolute real size of the object. Just from this image, for example, and we cannot exactly know whether this is a real thing or a bunch of toys, as we do not know the exact size of the vehicles from just this image. Okay. So to solve this issue, we apply IMU. Okay, to solve the scale issue. IMU is the equipment on your mobile phone, like I just mentioned, and you can use IMU and to estimate your car's motion and even your motion, and while you are walking, and when you use Google or Apple Map, you're driving or walking. Okay, we want to fuse IMU together with camera by enforcing the estimated pose from the camera and the IMU to be consistent. Here, the fusion is dynamic, and for every 2 consecutive frames, and the constructed pose consistency can dramatically penalize the derivation of the pose from the IMU sensor. Okay, which means, okay, if the scale is not correct, and we will from the camera side, and we will use this IMU to correct it as a constraint. And another advantage is that if you really look at root images, for example, and those kind of root images, their color is similar as well. Okay, and in this case, they're matching their spectral loss, which means their difference in the intensity is also small from one pixel to another pixel. That may result in some wrong matching between frames. In this case, with the IMU as the correct as a kind of constraint to the relative pose, we can get to better training for the network, for the postnet training. And with a more accurate postnet training, and actually we can get the point cloud more accurate as well, because here, actually they are constraining each other. So point cloud and the pose are constraining each other. So this is some of the apple tree root modeling result, and 1 year apple tree. Every 2 images are from the same apple tree. This is from one and from 2 different angles. This is another apple tree root. This is another apple tree root from 2 different perspectives. This is another one. Okay, we can see, we can relatively get, even from the images from mobile phone, you can get 3D structures relatively accurate and in details. Okay, and those some other type of rules. These 2 are the sweet potato, apple tree root, grass root. And if we compare with other state-of-art algorithm, for example, this SCSFM learner, and is also published on one of the top journals in computer vision in IGCV, and some other model depths or model depths 2, those are top conferences or journals. And actually, we can see our result is much better than many other results here showing from other algorithms. And we also tested the same algorithm for the above ground part, which also shows it works. So in many cases, users don't really capture video, but just want to take an image to model the routes. Or sometimes they just want to quickly process images of many routes, and each route just has 1 image. So in this case, we just have 1 image, what we can do. Okay, in So we train the system to make it possible. And here the system accepts an image, one image, okay, as the input. And there are two directions. One direction is called direct single image depth estimation. And the other one is view synthesis, okay, and which we call synthetic reconstruction, okay. With those two branches, and we want to fuse the results, 3D modeling result. Eventually, we want to get accurate point cloud for the roots. And this result is actually published in one of the top journals in image processing and in computer vision, and also in the entire computer science and engineering domain. This is one of the top ones as well. So that is the basic structure, the basic idea. And we can see here there are more details and the overall structure of the proposed plant root reconstruction pipeline. So from these two images, actually, we are really using camera 1 and camera 2 and to build a network and to estimate the depth directly from one image, for example, for this image to train the system, okay? And at the same time, we use camera 1 and camera 3 together to train another system, and which is actually under the GAN structure to predict the image from another perspective. Okay, and after that, we want to fuse them together. We want to fuse the two depth image together so that we can get the 3D structure. So talking in details, talking different details. So here, single image depth estimation, okay, which here is regarded as a 2D image reconstruction problem. And by projecting the image from the left view to the right view, okay, projecting, we here using the left image to predict the intensity, to predict the left image disparity. If the disparity is accurate, and with the left image, we can actually reconstruct the right image very well. And the same, using the right image, if we predict the disparity for the right camera, for the right image very well, and together with the right image, we can recover the left image very well. So in this way, we can actually regard the 3D reconstruction depth estimation problem as a 2D image reconstruction problem. From 3D reconstruction, depth estimation, and transfer that into a 2D image recovery problem. Okay, so sometimes we cannot hear from the left image, we cannot really build output a very accurate disparity, and that doesn't matter. Okay, and that is actually the purpose of training. And when we have a less accurate disparity together with the left image, we'll predict the right image not really correct. Okay, but we compare with the predicted and the reconstructed right image together with the original image until the loss is very small. Okay, the same for the other direction from right image to the left image. Okay, so this is the one direction, and another direction. Actually, after we train, okay, we train when the loss is very small, we can use one image to output a disparity very accurate. And for many of you guys, if you know stereo reconstruction, disparity means depth when you know the camera intrinsics. Okay, it's one-to-one mapping. And in the other direction, at the bottom, that is the synthetic stereo network. Here we train a generative adversarial network to predict the image from different perspectives. In this case, for example, this image and this image, and we can predict, okay, we train this one, and whether I can predict another view image very accurately. And if that is predicted accurately and compared with the original right image, and the loss will be small, their difference will be small, okay? And otherwise, we will continue to optimize the neural network until the loss is very small. We can predict another image. So there are some traditional GAN loss, and which I don't want to use too much time to explain what is GAN here. But on top of the GAN, and we actually, on top of the GAN loss, normal GAN loss, we here actually try to use the prediction and compare the original image and to see whether the disparity is small, the difference is small, okay? And essentially, once we have this neural network trained well, we can use one image to predict another image, the view from another image accurately. So in that case, we can do the stereo reconstruction. Okay, from one perspective to another perspective, stereo reconstruction, we can get another depth image. Okay, so once we have those two depth image, and we can fuse them together. Here, the basic idea of fusion is actually seeing, okay, if one depth image and it appears in another depth image, or their 3D reconstruction 3D point is very close to each other, we consider that is consistent. Okay. However, if one point appears in one direction from this AgRA, from this branch, but the same point does not appear from the other branch reconstruction result, in that case, that point might be correct, but at the same time, it also has a high likelihood that point is wrong. So eventually, after fusion, we get complete point cloud, 3D point cloud for the root, and which should be more accurate. So this is some reconstruction result actually, and we can see from the view. And here is just it's showing here we are rotating because we want to show everybody what the roots look like. And here is just, but in practice, we only use one image as the input. And we can see here our estimation, final estimation, is much better than those kind of other top conference papers and top computer vision and machine learning papers and in recent years. And even for those results, and they are much better actually. After fusion, we can see, okay, the result is actually even better than those two as well. But still, they are not too bad. But still, compared to the fused one, that is less. Okay, this is another example. With the one image input, we can do the reconstruction using mobile phone image, one mobile phone image. Okay, we can reconstruct the root structure. Okay, so that is using the mobile phone. Now let's move to another topic: root reconstruction using GPR, ground penetrating radar. Okay, so why we want to use ground penetrating radar? So if you want to use a mobile phone, we still need to take out of the roots, and which may harm the root functions. In that case, how to detect the root branches beneath the ground and reconstruct the root shapes without destroying them. So that is motivate us to use ground penetrating radar to reconstruct the root. Okay, so ground penetrating radar has already been used before, but most GPR ground penetrating radar sensors has restrictions on the scanning direction and the root position, and it's also very difficult to build the root models, and especially when the root model is complex. So instead, the majority work right now using GPR is to detect rough position of the roots. More challenges sensitive to noise, difficulty in the signal interpolation and sparse, and also GPR signal is sparse as well. So first, if you don't use GPR before, what is GPR? So GPR sends radar signals to the ground, okay, and which goes through the soil. When the signals meet obstacles, for example, and this signal will be returned, and the GPR sensor will receive that radar signal. So when the GPR is moving, and that makes this kind of parabola shape, and that is actually, we call that B scan. And each of these signal distance is actually A scan. But when the GPR is moving, that generating a parabola shape, that is actually called B scan from the GPR. Okay. So we want to use GPR, and first we want to detect, and after detecting the GPR signals for the roots, and then we want to do the reconstruction. So here we develop a new deep neural network based on GPR curve detection and root reconstruction method, and from the B scan of the GPR sensors. Okay, this is the overall structure, and it composes two network. The first one is like in the green part, and that is called Parnite, which means that is a parabola shape, parabola detection net. And the second part is GRECnet, and which means graph reconstruction neural network. And this paper is published in WACV 2000 last year. So first, we need to do pre-processing for the GPR signals, and which means we need to remove some noise signals, and this has already been applied to many GPR sensors as well. So it's just trying to make it clean, okay. And after that, with a cleaner, with pre-processed GPR images, and we want to move those kind of GPR images and to another neural network, which here we call that as a PARNet. Okay, this is the PARNet, and the meaning parabola detection network. In comparison with many other detection tasks, GPR B-scan mainly has a fixed parabola shape. Okay, so we can make use of this prior information to enhance detection accuracy. So in this case, actually, the detection is split into two subtasks. One is the parabola center localization neural network, and which means here, for example, and the other one is actually the parabola curve fitting neural network. Okay, so for these two, we want to make use of them to compensate each other. First, we want if the detection is accurate and their offset, their local offset is actually accurate, and then the parabola shape fitting is accurate. And in the other side, if the parabola shape is fitted well, and that means the detection, the center is actually detected well. So we want to compensate each other using those two subsets of the neural network. Okay, and to do three tasks, and those three tasks are related, we can consider that is a multitask learning. Okay. So once the detection is done, okay, and then we want from the right side, we have a sparse input. And with this sparse input, we develop another 3D reconstruction neural network, which using graph neural network and the multi-layer perception to interpolate. Okay, so it can take the 3D sparse point from the detection as input and to a graph neural network. And the graph neural network will analyze the geometry relationship between those points. Okay, and those geometric information will be passed into another neural network that is multi-layer perception, and the multi-layer perception will accept this kind of geometry information and fill in the gaps between the points based on this geometry information. And eventually, based on this graph and based on the graph passed to another layer, and we can do the reconstruction, we can do the interpolation of the neural net of the root structures. So this is some result. And the first part is the root detection result. And we can see with the input of the GPR signals, and our result is we can detect those parabola shapes very well. And in comparison with many other papers on AgRA and on remote sensing, robotics, and remote sensing conference and journal papers, their detection is actually less accurate. Sometimes the same one bounding box can bound multiple GPR signals, and at the same time, some are missed as well. And most important thing is once we detect these kind of parabola shape GPR signals, we know where they are exactly. We know the root, but we know the exact root position. Instead, compared with those bounding boxes, we just say, okay, that bounding box, that object is in the bounding box, but we don't know where it is. Where is exactly in the bounding box. Okay, that is one thing. Okay, after detection, we use this input, the sparse point as the input, and do the reconstruction. This is our reconstruction result with this input, which is pretty close to the ground truth in comparison with several other point cloud interpolation neural network. And we can see this sparse point cloud, we can get the result, and which is close to the ground truth in comparison with some other methodologies. Okay. So those are for the below ground, beneath the ground part. Now let's move out from the beneath ground to above ground. And so we are talking about here is using the low-cost UAV to do the 3D reconstruction. So right now, we want to first introduce the main methodologies and the sensors for the above ground part, and for range sensing and for 3D structure sensing. And the first what we want to introduce is the structure light. Most widely known is structure light sensor is actually Kinect. Okay, basically, if you play computer games, and probably you know Kinect. Okay, and the basic idea is the sensor, the structure light sensor project IR patterns to the object. And another IR camera captured the IR pattern. Based on the pattern shape and size, the sensor can estimate depth. That is one type. And the second type is actually time of flight cameras. And there are many types of flight cameras. Most cameras are based on their own, many companies has their own time of flight cameras. The basic idea is to measuring the traveling time of the IR light and in order to estimate the distance. So in general, LiDAR is also a type of the, for example, here, LiDAR is also a type of the TOF time of flight sensor, but most of the time people want to direct call it a LiDAR, and because it has been used a lot and has quite a lot of special properties for the LiDAR itself. For example, LiDAR usually has a higher valid range than structure light and some other cameras, and the LiDAR quite a lot of time is accurate as well, more accurate as well. And compared with the IR signals, for example, Kinect and the LiDAR is not affected by the nature IR signals, so you can use it in outdoor environment. Okay, so that is one of the reasons quite a lot of UAV right now are equipped with a LiDAR and the camera as well. But LiDAR has its own limitations as well. So, well, LiDAR is very expensive, and well, it's accurate, but it's also expensive as well. So, for example, this one, and the 60 beam LiDAR, value the LiDAR, is cost $80,000, and which is heavy as well. Okay, and even for this kind of high-end LiDAR, and it's still sparse compared with cameras. So that motivates us to propose another solution which can reduce the cost of the LiDAR. And so here we want to propose to make use of the benefit of the color cameras, and which has quite a lot pixels, has high resolution, and at the same time we want to coupling that with the 2D LiDAR. 2D LiDAR is also accurate. The only main problem is it doesn't have high resolution, which means it only has one beam of the LiDAR. We want to use those two sensors together and compensating each other so that we eventually. Hello? Sorry? Okay, probably I think I can move forward. So this is some comparison. 3D LiDAR and from the same company of the 2D LiDAR, and this is the RGB. We can see 3D LiDAR, even from the same company, that is much more expensive and than 2D LiDAR, than color cameras, and they are much heavier, and the power consumption for the 3D LiDAR is also much higher than the 2D LiDAR and the color cameras. So the only main thing here for the 2D LiDAR is very sparse. It just has one beam. And this still sends the 3D signals. It can still measure the 3D position. But the problem is that it shoots as a 2D array, okay, and outside, and only one beam. That is a major issue. So to make use of the both 2D LiDAR and the color camera, and we want to first calibrate the LiDAR and the color cameras so that we know the relative position in between and transform from one sensor's output to another one. This is basically the basic diagram, and for us to do the color camera and the 2D LiDAR calibration, which require to find the correspondences between the color camera and the RGB image. And essentially, we want to finally get the rotation metrics and the translation metrics as well. So this is the basic structure, and in detail, this is the process of calibration. We will use a checkerboard and to facilitate the process, as checkerboard can easily distinguish lines and corners. Okay, and once we have for each vertical line, we use a pencil to move along. Okay, and for example here, using the pencil to move along, and once we find a point, okay, if there is a LiDAR signal from the 2D LiDAR, and we mark this point, and actually when you see, okay, there's some distance, there is some spikes when you see, okay, on the 2D LiDAR screen, that means there's some distance change. Okay, when there's distance change, we mark this distance. That means we mark this position. That means we have in this position we have a 2D LiDAR signal. Okay, we continue with this process, moving along the vertical lines. Okay, and mark multiple points, and so that we can build correspondences between the 3D LiDAR position and the 2D image position. Okay, and eventually we get quite a lot of 3D points and from the 2D LiDAR on the 2D image as well, since we mark those positions on the image, and the camera can capture those positions. Then in practice, we will use multiple checkerboard to find the LiDAR points on different checkerboard planes, and the checkerboard for surface, which forms a LiDAR plane, like here, a LiDAR plane. Okay, once we have those 3D to 3D LiDAR to 2D image correspondences, we will use the algorithm called effective PNP, perspective endpoint. And finally, with the perspective endpoint, we will get rotation and translation vectors, and then we can get to know, okay, how can I translate from the LiDAR to the camera? Okay, we can align them together. And this is some example and from the 2D LiDAR, and this is 2D LiDAR position, and that is how we map those 2D LiDAR position on the real scene, and which is captured in this image. Okay. So once we have the single beam LiDAR and the color image calibrated, we want to have it used for the crop structure sensing on the UAV, okay, using the image and using the one beam LiDAR. And in this process, the color image will first be the input to the depth estimation network, which output the depth map, okay. And here is the same as similar like what we already introduced, using the left image, and we predict depth image, and which here is actually disparity. And if the disparity is accurate, and then we can recover the right image. And here we do that in multiple scales to make it more accurate and make it scale invariant. Okay, and this is one part, using one image and to output the depth image. Okay, and in real application, when we train, we use left image and the right image. But in real application after training, we just using one image. That is all we need. Okay, so once we have the depth image and we have the calibration matrix between the 2D LiDAR, and then the next step is to adjust using the 2D LiDAR to adjust the depth information. So we have the estimation from the color image, we have the 2D LiDAR, and we know which 2D image correspondence is actually corresponding to the image. So we know where they are corresponding to the depth image as well. So both depth map here and the LiDAR points will be input to a multi-layer perceptual neural network like here, okay? And the single beam LiDAR will be used to update the neural network and correct the pixel level, I would say the pixel level scale for the depth. So once the network is updated, it will be used to update the entire depth image. For example, in this way, right now we take the input, okay, and after several epochs, first epoch we update a little bit about the depth image and update to make the corresponding depth from the image estimate to be close to the 2D LiDAR estimation. And after the network, and until some time, it updating in and updated depth image from here, from the color images is very close to the 2D LiDAR. And once that is trained, and we will use this neural network to update the entire image, okay, to update the entire image. And this is some experiment result. And for example, for the crop field, one image and what is the output, and from the UAV images from two different perspectives, we can see even this image is actually has quite a lot of repeated patterns. We can recover the 3D structures very accurately for the crops. Some more images. And in comparison with some other methodologies, and which has quite a lot of ambiguity between the pixel coordinate, pixel matching, and actually which result in quite a lot of distortion, and our result is better. And actually we use it, we actually use the 2D LiDAR and the images, and back to one was in RIT, and we use it in a stick LiDAR challenge across the USA. We are one of the winning teams. So we use it for the other applications as well. For example, here my student is walking, and this is a single beam lidar. We can accurately estimate what is the distance of the person. And this is one application, and this is in the road application as well. And we can detect based on the lidar beam and the image what is the object distance away from the camera. So we also apply that into some other applications. And for example, this is using the one beam lidar and the image to estimate the camera. Okay, at the same time, I estimate the camera motion, and at the same time, we build the 3D maps and for the city. Okay, I might need to accelerate a little bit. And you can see here, I can skip a little bit. So for example, here, eventually, this is the map we built for this street. And you can see here, zoom in. If we zoom in, we can see, okay, this 3D structure corresponds to this image, and which shows it's relatively accurate. This is another demo. Well, the camera is moving, and we estimated the camera motion. At the same time, build the city map in real time. You can skip a little bit to accelerate a little bit as well.
Cool. I just want to know, this is your own acquired data or just from the public data set?
Sorry? Public. This is public data set.
Okay.
This is KD data set.
Yeah, looks like, yeah.
Later, I will show you our own data set as well, our own testing scenario.
Yeah.
Okay. So if we zoom in here for the map, we can see this is the zoom in street structure on the street corresponding to the image. So that is back to when I was in RIT. We test in the campus and we drive around the campus. And actually, if you look at this thing compared with the other two video, here there are not many buildings, and mainly that is road and trees and grass, which are actually not really textured. Okay, there are repeated textures, or there's no texture at all sometimes. So we can see with this kind of sensing and this RIT building, and with this kind of sensing and depth estimation, we can actually build the models as well, and for the campus. It's the 3D model, and after loading. Okay, this is the robot application that actually is right now is my planning right now to use it in the agriculture field. And we already have this kind of robot that is in my lab right now, and we actually show this robot dog, and we has a lidar, and that are two high payload rover robotics, and we have UAVs, and we have smaller size of the robotics. And right now we are planning in this summer and to equip the sensors on those kind of robotics, and trying to build the 3D crops from different perspectives, from above ground to beneath ground. And at the same time, for above ground, we want to use the bird view and the eagle view to build the 3D crops and fuse them together. These 3D crops, okay, 3D modeling and some other work, and like I have done something like the image fusion, and based on visible image and thermal image, and we want to fuse them together, and we develop a fusion network, and using GAN structure, for example, generating the images, and using discriminator 1 and discriminator 2, and to see, okay, whether fused image keeps the property and of the good properties we want from visible images, and whether we have the GAN structure can estimate keep the good properties from the infrared images as well. And for example, these some of the results. These are from visible images, these from the thermal images, and we can see actually from this region, and this is somehow visible in the air image. but not really. This chair is not quite visible. We can still see not very clear, but you can see still much better than the IR image for the chair. So sometimes RGB images has advantages in something, and some other thermal images and has other advantages. And here is another one as well. So. And we can see more details from the color images. But from the color image, this airplane is not very clear. But from after fusion, is much clear. And for the here is the same. And so from the RGB images and the thermal images, we can fuse them together to make more things clear. And these are some other examples as well. And you can see actually here in this region and. You can see quite clear in these RGB images, but you couldn't see very clear in this thermal image. But at the same time, this person is very clear in the thermal image, but it's not very visible in the RGB in the visible image. And this visible image is actually transferred into RGB. Into grayscale though. And here those details as well. So after fusion, we can keep the properties of both type of images. This is one type, and we also do segmentation, and we also do disease detection. Okay, so to conclude my work, and we use images in various modalities that could build dense 3D structures and the plant structure for both above and beneath ground part. And in different modalities could be modeled, and especially some low-cost mobile devices could obtain the comparable 3D sensing outcome as good as those complicated devices with the support of AI system, a specialized AI system, especially for those kind of crops and taking these crop properties. Okay. This is my sponsors and some companies, some federal funding. Okay. And thank you very much. And I would like to answer any questions or comments.
Yeah, thank you very much. Yeah, Dr. Lu. Yeah, such a fruitful achievements. Yeah, lots of work. Yes, around the 3D sensing. It's really good. Yeah. Anyone of our audience have some questions? Can ask from Dr. Lu. And yeah, for me, I have a little question. It's about that the 3D reconstruction from the structure from motion.
Okay.
A question is that here you use maybe some picture show that using 32 cameras. The thing is that how you control these cameras. I mean that to do the time synchronization for this.
Let me try to so from